Hi everyone. So welcome to the first installment of your Transformers module. By now I expect you would have already gone through the video from Learn Engineering that I posted with the animation of the Transformer. So you should have a basic idea of what the construction is and the uh, what the operation is like already, but we'll go through some of those things again in more detail. Now, by the end of this session, I hope you should be able to describe the construction and theory of operation of an ideal two-winding transformer and calculate primary and secondary currents and voltages given the turns ratio in an ideal transformer. So, to get started, what are transformers? These are static devices, static meaning there are no moving parts in it, as you'd have in a machine, a DC motor, an induction motor that we'll do later on in the course. And the purpose of it is really to convert voltages and currents from one level to another, either to raise the voltage or to drop the voltage, to raise the current or to drop the current. And you could find them in all ranges of sizes, from very small devices like these that you could mount on a breadboard to pole top transformers that you could see here, to large power transformers that you'd see in a substation. And you could see these are very large. You could probably stand underneath here without a problem. Some of these transformers actually have doors in them. You could take ladders in them to service them and so on. So these are the most expensive pieces of equipment in the power system apart from the generators, and they are absolutely necessary for power transmission, and that is the purpose we are interested in them for this course. So you'll see here a little bit about the internal of a transformer, and we have the core, which is the outside here, and the conductors wrapped around it. This is a three-phase transformer. You can see it's quite big. This one is 525 MVA, and this one is a 716 MVA, and you can see the size of a person here compared to the whole transformer. So even this presents a lot of challenges even in transporting it. You could see here the size of the transportation that is required, and just take a look at that compared to the size of the building here and the size of the cars. So these require these pose rather technical challenges, not only in terms of their operation and how you use them, but also in how you get them on site, how you prepare your foundation and so on, so that they don't just sink into the ground. You can't just put it on, a dirt foundation. So these are the kinds of devices that we are interested in, and for the purpose of this course, when we look at three-phase power, it is this size of transformer that we're really interested in. So why do we want them? From the previous video you should have looked at, you would see that one of the main things is that we want to change voltages and currents in the system, and we really want to do that because we want to reduce losses. As you know, losses in the system come about from resistances. So we have I squared R losses, as we call them. So when we change the voltage level, say we raise the voltage, the current would drop, and that will result in lower I and then lower power losses for the same amount of power that you want to transmit. Now, what about DC transmission? Could we do this? In the early days of power transmission, you couldn't, because there was no way to change the DC voltage levels. But now with the advent of power electronics, you could use things like buck boost converters, and you'll see people are looking towards solid state transformers and so on now. So that is something we're not going to cover in the course, but I just thought I should mention it so you could look at it if you are interested. which I hope you are, and then you could ask yourself, well, are these transformers still necessary? How does this change the way the power system operates? What does it mean for the types of machines we use, etc.? So, how do the transformers work? These work basically by electromagnetic induction, and basically what we have are coiled conductors that generate magnetic fields, and these magnetic fields, the magnetic field from one coil is coupled to another coil, and that is facilitated by the use of a core that you see here. So we have the primary winding. The primary winding is the winding that we excite, and so you'll have some voltage source connected here, and that voltage drives a current through the winding. And as you'd know from your right hand grip rule, if you have current coming in this way, then the flux that is produced should be this way, which is the direction we have here. So the flux is produced and it goes through the core and then returns. And remember, magnetic flux always flows in loops. It is not like an electric charge where the electric field goes out to infinity. The magnetic field must make a loop. So the principle we're working with here is the Faraday-Maxwell law of electromagnetic induction. So we excite one coil and we get a magnetic field. Since we excite it with an AC source, the magnetic field will keep on alternating. So in one case, the current is going this way, as I have in the arrows here, and the magnetic field will go up. And then when the polarity changes, the current will go the other way. And then when it goes the other way, the magnetic field will go down. So on the secondary side here, you will have an alternating field being experienced by the secondary winding. And according to the Faraday-Maxwell law of electromagnetic induction, when you have a changing magnetic field, then you're going to end up with an EMF being induced. In this case, the EMF will be curling around the conductors, and that is how we build up the secondary voltage, Vs. So the reason that the transformer is constructed like this is that we want to direct the flux from one point to the other. So when, as you know, if we have a straight conductor, then we're going to have the flux going around. So when we coil that conductor, when we make a loop with it, as we see here, then you get all these loops around. And if you add these up, what you end up getting is a linear magnetic field, a solenoid field. So that is the reason that we have the coils in the transformer. The next thing we want to do is we want to direct the flux to the next coil. So for that we use a core, and the core works pretty much like a resistor, low resistance path. Now if you remember from your 1015 class, when we talk about magnetic fields, we don't use the term resistance, we use the term reluctance. So it is actually a low reluctance path, and to understand what is happening, you could use a resistor analogy. So the air is a very high reluctance path, so it is like a high value resistor, and the core is a very low reluctance path, so it functions like a small resistance. So when we have these two things in parallel, the current would flow predominantly through the low resistance path, and that is basically what happens when you put in the soft iron core. The current flows through the core, the majority of the current flows through the core and is directed through the secondary winding and then returns. So, and the reason we want to do this is because the the flux is the thing that transfers the energy. So if we have a lot of flux in the air, it is not doing anything. It's not making its way to the secondary side. So we want to really direct it with a guide to the secondary coil. So we talked about before the Faraday-Maxwell law of electromagnetic induction, and you should know that from your 1050 notes and 1000 that this is the principle of operation of inductances. So far you would have probably encountered self-inductances, and these are when you have one coil. If you have a single piece of wire and you coil it, you know that the inductance of the wire increases. For the transformers, what we look at is mutual inductance, and for mutual inductance it is really the same category, except now you're not looking at the back EMF induced in a coil by a current flowing through that same coil, which is what you look at for an inductor. You have a coil of wire and the current flowing through it causes a back EMF to build up. What you're looking at now is a coil of wire, and it's going to induce an EMF in a coil somewhere else. So it is a mutual inductance because the current in this coil creates an EMF across this one, and the current in this one contributes to the EMF across the first one. So it is mutually inducing voltages. So you should be familiar with self-inductance, and you should know that E is equal to L di dt, where L is defined as the flux linkage per unit current. And if you are not familiar with this, you should revisit your ECNG 1050 notes and reacquaint yourself with it. For mutual inductance, it is pretty much the same, except now all the flux does not make it to the secondary. So when we have current flowing through a coil, you'll have some of the flux going through the secondary and some of the flux will not make it. This flux that doesn't make it, we call it the leakage flux because it leaks out of the secondary winding. Well, not out of the secondary winding, but it doesn't make it to the secondary winding. So if you think about a pipe delivering water to a tank, say, and you have a leak, the leaked water is the water that does not make it to the side that you want to deliver it. So this is the same thing that we're talking about. When we say leakage, it doesn't make it across to the point we want it to get to. So for the case of these two windings here, phi 11 is the flux from coil 1 that only links coil 1, and the flux that makes it to 2 is the flux from coil 1 that links coil 2. So the voltage, if you remember self-inductance, E is equal to L di dt, or E is equal to N d phi dt, which is the same as d lambda dt. If you remember this, all the flux here for self-inductance was linking the coil because it was the flux generated by the coil. For mutual inductance, since we don't have that, only the portion of the flux that does link the coil, phi 12, contributes to the voltage being induced. So we have the voltage in the secondary is N2, which is the number of turns in the secondary side, multiplied by phi 12, which is the flux linking sides 1 and 2, the flux generated by side 1 that makes it to side 2. Whereas the EMF in side 1 would be d phi 12 plus phi 11 dt. This would be V1 because all the flux links that coil. So since phi 2 is related to I12, is related to the current I1, then we could say that V2 is proportional to I1, or if we introduce a constant, V2 is equal to M di1 dt, and this M is the mutual inductance, as we will see now. So we know that V2 is equal to d lambda 1 2 dt, and we know lambda is equal to n by phi. So this, which we have here, is equal to d lambda 1 2 dt. So we could set this equal to this, and we could then get rid of these, and we will get M is equal to d lambda 1 2 di, which is flux linkage per current, which is the definition of inductance. But now the flux linkage is the flux linkage between two separate coils, which is why we call it the mutual inductance. Now, the ratio of the flux that makes it to the secondary side from the primary side, we use that to define a term we call the coupling coefficient. So it basically tells you how good the transformer is at coupling the primary side energy to the secondary side energy. So it is simply the flux that makes it across divided by the total flux. So you want a K that is as close as possible to 1, which would be ideal. And this brings us to the ideal transformer. For an ideal transformer which has no losses, which means no winding resistance, and has a coupling factor of 1, which means no leakage flux, that means that the flux on the primary side is equal to the flux on the secondary side. So we could say N1I1 is equal to N2I2, and then we could define I1 from this. We just cross multiply, we get I1 on I2 is equal to N2 on N1. And we could do the same thing with the voltage, and we have V1 is equal to N1 d phi dt, V2 is equal to N2 d phi dt, and then we could get the relation V1 on V2 is equal to N1 on N2. So we have V1 on V2 is equal to N1 on N2, which is equal to I2 on I1. So the V and the N, the number of turns, a higher number of turns is going to give you a higher voltage but a lower current. So this is what it tells you. So we represent this ideal transformer as simply two coils, and here we have the turns ratio. So when you have this symbol, basically what you're going to see is that whatever voltage is here, V1, will come out on this side. V2 is equal to N2 on N1 multiplied by V1. And whatever current you have here, I1, will be on this side, N1 on N2 I1, which will be equal to I2. So this is the basic transformation for an ideal transformer, no losses. So let's look at an example now. We have an ideal transformer with 90 turns on the primary and 2250 turns on the secondary that is connected to a 200 volt source. The load across the secondary draws a current of 2 amps. We have to calculate the value of the primary current and the secondary voltage. So if we draw a little diagram, we have 2250 turns on the secondary and 90 turns on the primary, and we know the primary voltage is 200 volts and the secondary current is 2 amps. So if I wanted to draw this with my circuit diagram now, I could simply draw it like this as well. N1 N2, and this would be 200, and this would be 2 amps. So I could draw it like this as well, and this is the diagram I would expect you to draw. I don't expect you to draw this for the course. This is just to show you what is happening. Now I want to calculate the primary current and the secondary voltage. So I know that I have these relations. I secondary on I primary is equal to the number of turns on the primary over the number of turns on the secondary, and this is also equal to the voltage on the primary over the voltage on the secondary. So I have the secondary current. I want to find the primary current. So I simply take this over to this side, and I get I primary is equal to 2 multiplied by 2250 or 90. Remember, if I'm going from this side to this side with the current, I have the N from the secondary side on the numerator. So that will give me 50 amps, and then I do the same thing with the voltage, except now I'm going this way, so I will have to do 2250 on 90 multiplied by the voltage. So I always go 2 with the voltage. The side I'm going to will be on the numerator. With current, the side I'm coming from will be on the numerator. So again, I use my ratios, my turns ratio, to simply go from one side to the next, and I work it out as 5000 volts. So I hope by now you should be able to describe the construction and the theory of operation of an ideal two-winding transformer and calculate primary and secondary voltages and currents given the turns ratio in an ideal transformer. Next, we'll be looking at the non-ideal transformer. That is what happens when we start to incorporate losses in the system.